Hello, this is Capt Chaudhari in my series of videos on marine astronomical navigation. Today I am going to talk about moon, particularly in reference to the altitude correction. Right, a general idea of altitude correction we have already covered in my last video. In this video we will see what are the special things which we do in respect of moon and why moon is special. Okay, now we had said that when the moon is at sensible horizon, right, the horizontal parallax is the angle when the moon is at sensible horizon, right, and it is the angle at that time subtended by the radius of the earth through the observer. It is very important to say radius of the earth through the observer. So we had also seen that as the moon rises in altitude, you can see this angle would reduce and the angle hypothetically will become 0 if the altitude was 90 degrees. So one of the corrections that we apply in case of moon is parallax in altitude. Now this parallax in altitude, that is this angle, is applied to the horizontal parallax because horizontal parallax into cos of apparent altitude is equal to parallax in altitude, which is always positive. Now in the almanac, for every hour we are given this horizontal parallax. Like I have exaggerated the shape of the earth. Earth is of oblate spheroid type appearance. Like suppose there is this observer at pole, then radius of the earth would subtend an angle at the center of the earth, is given by this angle. Whereas if we assume that the observer is at equator, right, we consider this angle that is subtended at the center of moon by the radius of earth through the observer who's at the equator. This angle is going to be large and this angle is going to be least, right? So what happens, we might be observing, or the horizontal parallax that is apparent to us from the various latitude will have a value in between. Now there is a table called reduction to horizontal parallax, and that table is in page 453 of Norris tables. So reduction means reduction to the horizontal parallax that is given every hour in the almanac. So the value of the horizontal parallax that is given in nautical almanac for every hour is for an observer who's at the equator, whereby the value of horizontal parallax is maximum, right? You know that value of horizontal parallax would be minimum if the observer was at pole, and for any intermediate latitude the value of horizontal parallax would be between this and this, but definitely it would be less than this, right? Less than what is given in the almanac, right? Because for any intermediate latitude, the radius of earth for measuring horizontal parallax will be in between these two radii, and that's why this correction is applied, which is called reduction to horizontal parallax. So that reduced horizontal parallax multiplied by cos of apparent altitude is the parallax in altitude which we apply, which is always positive. So reduction is negative, but parallax in altitude is always positive. Another interesting thing about the moon, there is augmentation of moon's semi-diameter. Any question that is asked to you about moon, if you don't know the answer, it would be safe to say because of close vicinity of the moon. If I ask you why the horizontal parallax or the parallax is large in case of moon, naturally it is because the moon is close to the earth, right? So the parallax in altitude is large in case of moon compared to the other heavenly bodies. If I ask you why there is augmentation of moon semi-diameter, you can simply say because of close vicinity of moon to earth. Suppose we say that moon is over here. Now purposely what I have done is I have exaggerated the size of earth compared to the distance of moon. and I'm showing that moon is not very far from the earth, which actually is the true compared to the other heavenly bodies. So what happens is augmentation of moon's semi-diameter. Let us say this is the observer and this is the plane of observer's rational horizon, and let's say this is sensible horizon, right? The distance from the center of the, let's consider the moon at a sensible horizon. Now this distance, which is the distance from the center of earth to the moon, decides what is the semi-diameter of moon, right? The semi-diameter of the moon is decided by the distance of the moon from the center of the earth. Now this is the value given in the almanac. So let us say SD1 is the semi-diameter given in almanac, and this semi-diameter is the one which will be observed from the center of the earth. Whereas just to talk about the semi-diameter at the time of moonrise, let's say the moonrise is happening and you are able to look at the moon, or let us say moon is at sensible horizon, right? This distance and this distance are not much different, because if you talk about this angle, this is just about a degree or maybe less than 1 degree. So can we say this distance is approximately this distance? So what semi-diameter you will see of the moon at the time of sunrise, let it be SD2, that is semi-diameter at moonrise, Thereafter, if the moon rises in altitude, you can see that the distance of the moon to the observer reduces, and when this distance reduces, right, the semi-diameter would increase. That means the semi-diameter which you witness at the time of taking the sight, at the time of taking the observation, is dependent on the distance that is much less compared to this distance, which is the distance from the center of earth to the observer being on the surface of the earth. So this semi-diameter is more than semi-diameter 1 as well as semi-diameter 2. How much more? So that extra amount of semi-diameter that we witness at the time of taking sight, that extra thing is called augmentation. And what we do is we take augmented semi-diameter in altitude correction. Once again, if you go to page 453, you will find there is augmentation given with the argument the altitude of the moon. So as the moon rises in altitude, the augmentation should increase because the moon comes closer and closer to an observer on the surface of the earth. I mean, this can be visualized like if you see a helicopter is maintaining an altitude on the surface of the earth, but when you look at the helicopter very far off, close to the horizon, you will find it appearing very small. But when the helicopter flies above your head, you find that it has become big in size, right? So moon's augmentation of semi-diameter is something like that. So let's do a numerical from my book, and this numerical is the moon's upper limb was 43 degrees 12 minutes. Sextant altitude, moon's upper limb was 43 degrees 12 minutes. And index error is 1 minute on arc. Index error is 1 minute on the arc. Height of flight 10 meter. In latitude 30 degrees north. The observation was done in latitude 30 degrees north, and the date given is 12th October. We'll try to understand the various corrections which are applied to this altitude correction. Say sextant altitude is 43 degrees 12 minutes. Index error 1 minute on the arc means negative, so it becomes 43 degrees 11 minutes. That is the observed altitude. Dip depends on height of eye, and it is always negative. So if we look at the dip for 10 meters, it is 5.6 minutes negative. 43 degrees 5.4. Now refraction. Stars, when you do the altitude correction, when you look at the altitude correction tables, you will find that the stars altitude correction is very small, because the altitude correction for star is given only for refraction. So if you want to know any other heavenly bodies, because refraction does not depend on the body, refraction depends on the altitude. So if you want to find out what is the refraction correction, you should look at the total correction of star. So when we look at the total correction of star, we find the altitude corrected by 1 minute. So refraction is always negative and it is 1 minute, so we get 43 degrees 4.4 minutes. Now what semi-diameter I pick up from the almanac, like it is given at the bottom of the page for all the 3 dates. So if I pick up the semi-diameter at the bottom of almanac, what I get is the semi-diameter as would be seen from the center of the earth. But I explained you the process of augmentation, why the augmentation is there. So there is a table in Norris table, page 453, I told you. There you will find the augmentation depending on the altitude, and that augmented semi-diameter of the moon was 15.3 minutes. And because it is upper limb, I would subtract the correction, and I get 42 degrees 49.1. This is augmented semi-diameter. Now if you look at the nautical almanac, right, for every hour, every GMT hour, you will find the horizontal parallax is given. This horizontal parallax which is given is horizontal parallax as would be witnessed from the equator. But we are on 30 degrees north latitude. So we have to look at the table, that is reduction in horizontal parallax given in page 453, and you will find that if you apply that reduction, which might be very small, 0.05 or 0.1, you apply that reduction is negative, and that reduced horizontal parallax multiplied by cos of apparent altitude will give you the parallax in altitude. And when you do that, you will find that the parallax in altitude is 40.45. And parallax in altitude is always positive. So final true altitude that I get is 43 degrees 29.55, right? So this is the true altitude. If you want to find out total correction from the nautical almanac, right? So in the nautical almanac, the horizontal parallax is given the value to look at the table. You don't look at the semi-diameter. Why you don't look at the semi-diameter? Because horizontal parallax actually is a function of semi-diameter. It's like this is the earth and suppose this is the moon. If you say that this is the horizontal parallax, right? If you say this is the horizontal parallax, then the angle that is measured from the center of earth, this one is the semi-diameter. So if the horizontal parallax increases, semi-diameter will increase. If the horizontal parallax decreases, the semi-diameter will decrease. So when you look at the table for total correction of moon, it gives you consolidated correction. If we go by the total correction table, what you will get is the observed altitude after you apply the index error, and then when you apply dip, you will get the apparent altitude. To the apparent altitude, when you go to the total correction table, you will find the main correction and additional correction. Now both these corrections are positive, right? If you had taken earlier the lower limb, you would get the answer straight away. But if you had taken upper limb, towards the end, you will minus 30 minutes. That is the procedure when you are using the tables.